Hello everyone, the subject is EC3501 Wireless Communication. Third unit is Modulation Techniques, Equalization and Diversity. Now we are going to see about the topic equalization. These are the topics in the third unit. Now let's see about equalization. There are three techniques. They are used independently to improve the receiver signal quality. The three techniques are equalization, diversity, and channel coding. In equalization, we have linear equalization and non-linear equalization. In diversity, we have spatial diversity, polarization diversity, frequency diversity, and time diversity. In the case of channel coding, there are two types of coding. One is block codes and another one is convolutional codes. So equalization, it compensates for inter-symbol interference, that is ISI, created by multipath with time dispersive channels. So in equalization there are two types. One is linear equalization and another one is non-linear equalization. And second one is diversity. It also compensates for fading channel impairments and it is usually implemented by using two or more receiving antennas. There are four types of diversities. One is spatial diversity, second one is polarization diversity, third is frequency diversity, and fourth one is the time diversity. So equalization, it counters the effects of time dispersion, while the diversity reduces the depth and duration of the fades experienced by a receiver in the flat fading channel. And the third method is channel coding. It improves mobile communication link performance by adding redundant data bits in the transmitted message. It is used by the receiver to detect or correct some of the errors introduced by the channel. So there are two coding methods. One is block coding and second one is convolutional coding. Now let's see the fundamentals of equalization. The term equalization can be used to describe any signal processing operation that minimizes inter-symbol interference. There are two operating modes for an adaptive equalizer. The first mode is training and second mode is tracking. There are three factors that affect the time spanning over which an equalizer converges. The three factors are equalizer algorithm, equalizer structure, the time rate of change of multipath radio channel. So TDMA wireless systems are particularly well suited for equalizer. An equalizer is implemented at baseband or at IF in the receiver. Since the baseband complex envelope expression can be used to represent baseband waveforms, channel response and demodulated signal. So this is the block diagram of a simplified communication system that uses adaptive equalizer at the receiver. So equalizer is used at the receiving side. And now let's see about the equalization techniques. Now let's assume x of t is the original information signal. F of t, it is the combined complex baseband impulse response of transmitter, channel and RF IF section of receiver. So the signal received by the equalizer is represented by this equation y of t. In this equation we have f star of t, it is nothing but complex conjugate of f of t, and nb of t, it is the baseband noise at the input of the equalizer, and the operation here we are using is convolution operation. If impulse response of the equalizer is Heq of t, then the output of the equalizer is given by this equation. In this equation we have g of t, it is a combined impulse response of the transmitter, channel, RF or IF section of the receiver and the equalizer. So this expression, it indicates the complex baseband impulse response of a transversal filter equalizer. Here the parameter Cn, it is nothing but complex filter coefficients of the equalizer. So if we assume that the noise is equal to 0, that is Nb of t is equal to 0, then in order to force this expression, this is the condition, and now the goal of equalization is to satisfy the above equation. In frequency domain, the above expression can be expressed as follows: H equivalent of f into f star of minus f is equal to 1. Capital H, it indicates the Fourier transform of H EQ of t, and capital F, it indicates the Fourier transform of small f of t. So this is the basic structure of adaptive equalizer. So adaptive equalizer, here it is, we have a time varying filter which must continuously be retuned. So the input signal is applied, and here we have the several elements, delay elements are present, an adaptive algorithm that updates the weight of each filters. And here in the above diagram, there is a single input. It is denoted by Yk. The value of Yk, it depends on the instantaneous stage of radio channel and specific value of noise. And this Yk is a random process. Adaptive equalizer structure is called as transversal filter. It has n delay elements, n plus 1 taps, and n plus 1 tunable complex multiplier called weights. Weights are updated continuously by the adaptive algorithm. And let's see the different types of equalization techniques, that is survey of equalization techniques. Equalization techniques are classified into two categories. One is linear and second one is non-linear. If the reconstructed message data, that is D of t, is not the feedback path to adapt the equalizer, then the equalization is called as linear equalization. If there is feedback path, then it is called as non-linear equalization. And these are the several types of equalization techniques. There are linear and non-linear. Under linear we have several types, and under non-linear also we have several types of equalization techniques. So let's see about linear transversal equalizer. It is, in short, it is denoted by LTE. It is the common equalizer structure. It is made of tapped delay lines with tappings spaced a simple period Ts apart. So this is the basic structure of the linear transversal equalizer. There are delay elements and there are taps. So here we have to see about two different types of filters. One is FIR filter and second one is IIR filter. FIR filter, it is the simplest LTE that uses only feed forward taps, and the transfer function of the equalizer filter is the polynomial in z power minus 1. It has many zeros but poles only at z equal to 0. In the case of IIR filter, here we have equalizer has both feed forward taps and feedback taps, and the transfer function is a rational function of z power minus 1. It has many poles and zeros. So this is the tapped delay line equalizer filter. It has both feed forward and feedback taps. This is the diagram. This is the circuit diagram or block diagram of tapped delay line equalizer filter. Next, let's say about linear equalizer. It is implemented as an FIR filter. Otherwise, it is known as transversal filter. The current and past values of the received signal are linearly weighted by the filter coefficient and summed to produce the output. So this is the structure of the linear transversal equalizer. We have the delay elements, we have the taps, we have the weights, and we have one more device, that is threshold detector, and finally we have the output. Output is denoted by dk. And this linear equalizer can also be implemented as lattice filter. This is the structure of the lattice equalizer. And now let's see the characteristics of lattice filter, or the advantages and disadvantages of lattice filter. The lattice filter, it has numerical stability and the convergence rate is fast, and this is a unique structure that allows the dynamic assignment of the most effective length. But there is one disadvantage, that is the structure of the lattice filter is more complicated. Now let's see about the nonlinear equalization. Nonlinear equalizers are used in applications where the channel distortion is too severe. There are three effective methods. One is decision feedback equalization, second one is maximum likelihood simple detection, and third one is maximum likelihood sequence estimator MLSE. Now let's see about DFE, that is decision feedback equalization. The basic idea behind this decision feedback equalization is, once an information symbol has been detected and decided upon, the ISI that it introduces on future symbols can be estimated and subtracted out before detection of subsequent symbols. and it can be realized in either transversal form or as a lattice form. This is about the decision feedback equalizer, and this is the structure of the decision feedback equalizer. Here we have the feed forward filter, that is triple F, and then we have the feedback filter. It is denoted by FBF. The input is denoted by Y and the output is denoted by D. And the second one is predictive DFE. It consists of a feed forward filter and feedback filter, and the latter is called noise predictor. The predictive DFE performs as well as conventional DFE as the limit in the number of taps in triple F and FBF approach infinity. FBF in predictive DFE can also be realized as a lattice structure. RLS algorithm can be used to yield fast convergence. So this is the structure of the predictive decision feedback equalizer. Here we have feed forward filter, feedback filter, and then we have a decision device. We have the summer, and the received signal is applied and the final output can be obtained at the other end. And next we have the maximum likelihood sequence estimation equalizer, MLSE. MLSE tests all possible data sequences rather than decoding each received symbol by itself and chooses the data sequence with the maximum probability as the output. Usually has a large computational requirement. It requires knowledge of the channel characteristics in order to compute the matrices for making decision. It requires the knowledge of statistical distribution of the noise corrupting the signal. So this is the structure of the maximum likelihood sequence estimation or MLSE equalizer. And there are algorithms for adaptive equalization. So the performance measures of adaptive equalization algorithms are rate of convergence, misadjustment, computational complexity, and numerical properties. The factors that dominate the choice of an equalization structure and its algorithm are cost of computing platform, power budget, radio propagation characteristics. So the algorithm for adaptive equalization, let's see that the speed of the mobile unit determines the channel fading rate and Doppler speed. So the choice of algorithm and its corresponding rate of convergence depends on channel data rate and coherent time. The number of taps used in equalizer design depends on maximum expected time delay spread of the channel. The circuit complexity and processing time increases with the number of taps and delay elements. So the algorithm for adaptive equalization are given here. There are three classic equalizer algorithms. First one is zero forcing algorithm. Second one is least mean square algorithm. And the third one is RLS algorithm. RLS is nothing but recursive least square algorithm. So this is taken from the textbook Wireless Communication by Rappaport. Thank you.